Hello, my name is Humberto Cifuentes, and along with my partner Vera Kenny, we will be going over the automatic exposure control chamber. The AEC is a function inside of the X-ray room that helps us achieve our two main goals as radiographers, and that is achieving the best or highest quality image and minimizing patient exposure. There are 4 systems inside of the AEC that help us achieve these two goals. The first one is ionization chambers versus phototimers, density control, minimum response time along with backup time, and final considerations, which involve selecting the correct detector, patient positioning, and collimation. These 4 things help us achieve our best possible image, and they help us minimize patient exposure.
Good morning, my name is Vera. I'm going to explain the differences between the phototimer and the ionization chamber. So, the purpose of the AEC chamber is to trigger automatic termination of the X-ray photons when a preset amount has been determined.
Nice.
To quote Johnson and Faber, radiation is transmitted through the patient and converted to an electrical signal, terminating the radiographic exposure. So there are 2 devices that do this, the ionization chamber and the phototimer. When using the phototimer, light paddles coated with fluorescent material along with a photomultiplier tube convert the radiation being received into electrical energy. With the phototimer, the light paddles are placed behind the image receptor. So the radiation hits the image receptor before getting to the light paddles and being detected by the sensors. The ionization chamber, on the other hand, makes use of a hollow cell filled with air, attached to a timer circuit by an electrical wire. When exposed to the X-ray photons, air in the cell becomes ionized. The electrical charge produced travels to the timer circuit via the electrical wire. When the predetermined amount is received, the timer is alarmed and radiation exposure is stopped. Here's another example of the comparison between the ionization chamber and the phototimer. To reiterate, the ionization chamber shown on the left is filled with air and connected to a meter and an exposure switch. When exposed to X-ray photons, the air in the chamber becomes ionized, sending an electrical signal to the meter. When the meter receives a predetermined amount of radiation, the exposure switch is activated and the radiation ends. The ionization chamber is positioned on top of the image receptor. X-ray photons must come in contact with the chamber before the image receptor. This makes the ionization chamber an entry-type device. On the right, the phototimer uses fluorescent-coated paddles that convert the X-ray photons into light photons. From this point, the photomultiplier tube converts the light into an electrical charge and sends it to the meter. Once again, when a sufficient amount is received at the meter, the exposure control automatically stops the excess radiation. The fluorescent screen and the photomultiplier tube are positioned behind the image receptor, so X-ray photons must exit the image receptor before being detected by the chambers. This makes the phototimer an exit-type system. In both systems, the electrical charge is always proportionate to the amount of radiation received. Although the ionization chamber is less sophisticated and less accurate than the phototimer, it is most commonly used because of the decreased chance of failure.
Another key factor in the AEC is density control. Density control allows a radiographer to change the amount of density, or MAS, on the fly. If we take an image and we know that that image is underexposed, we need to increase the density. So on most modern machines, you'll have panels for the tube, for the X-ray, that on the panel you'll see a group of numbers like this. Usually you'll see from -2 to +2, but there are some that go from -5 to +5. And what these numbers represent is an increase in MAS for that image. So for example, if we're at set 0 and we go to +1, that means that we're doing a positive 25% increase. And +2 would be 50 increase. So you could take that, if we had a positive 4 on here, it'll be 100%. So the same goes for these on the left as well. Negative 25%, negative 50%. So if we have an image that's underexposed, what we're going to do is increase it, let's say on a scale of 25%, so that we have an image with a little bit more exposure, and that means that we'll have a darker image. All right, so if we take what we just learned about density control and apply it to a real life scenario, it'll look something like this. In AEC controls, or if AEC controls are in 25% increments, if a normal AEC exposure of the lumbar is at 40 MAS, a repeat exposure at +2 would yield an MAS value of, so what we just learned is that, and it holds true, 25% increments, right? That means that 50% increase of 40 MAS would lead us to an answer of D, 60 MAS. And that is how, on the fly, you can take a underexposed image to a good amount of exposure in just a couple of turns of a knob. Another component of the AEC is backup time and minimum response time. These two features are involved in an AEC and implemented in an AEC to help us get the best high quality image while minimizing exposure to a patient. So the best example for minimum response time would be getting your machine to crank out an image as fast as possible. So today with most modern machines, or not most, but a few, you have a minimum response time of 1 millisecond. So that's basically the machine can crank out an image, generate an image in 1 millisecond. This is especially useful in pediatric patients, geriatric patients, or anybody with a condition that they can't stay still. That is the #1 reason why you would want to decrease minimum response time. According to Faber, backup time is the maximum length of time the X-ray exposure continues when using an AEC system. So what that means is we would cap it, usually it goes from 150% to 200%. So if we set an exposure at X amount, then the cap would be at 200% of that time, or of that amount. So if it reaches either an MAS or a time that reaches that cap, the machine will just shut off. And we do this for two things. And we get back to the same thing that are the cores of a RTR. Getting the best possible image and patient safety. You don't want to expose a patient to too long of a time, and you don't also want to damage your equipment. If you have the X-ray tube heated up for too long, the backup time is there to shut it off, essentially. If there is no backup time and there is a mechanical error, essentially the tube could stay on and pretty much everything will melt.
Like my partner just said, one of the most important elements of using radiation in medical imaging is reducing patient dose as much as possible. To do this, it's important to consider the collimation of the X-ray field, the size and selection of the detectors, and patient positioning. So please follow me into the X-ray room. Thanks for joining me in the X-ray room. Here's the control panel that controls the X-ray tube. If you come in a little bit closer, you can see that the AEC control has 3 chambers to select from. The AEC control has 3 configurations. Of these 3 configurations, there are 7 possible combinations that you can choose to create the best image for your patient. This will be the first one, this will be the second, and then this is the third. It's possible for you to choose the first and the second, or the first and the third, or all 3. When choosing the combination that you want to use to create an image, the selection is important because if the body part is not covering the chamber completely or leaving one of the chambers out that you've selected, radiation can proceed to the chamber and set off the alarm prematurely, and the patient has to be re-exposed again. If the patient is not covering the chamber completely, like in this example, and radiation can seep through the body part, terminating the procedure prematurely, meaning that the patient will have to be exposed once again. If the body part cannot cover the selected detectors completely, then the AEC chamber should not be used. So that's all, guys. We've explained the purpose of the AEC chamber along with its 4 key components: phototimers versus ionization chambers, density control, minimum response time and backup time, and final considerations when deciding to use the AEC chamber. More often than not, the AEC chamber is a great asset that can assist us to produce a high-quality image while keeping patient dose as low as reasonably achievable.
Thanks for watching, everybody.
Bye! That's weird.